Western civilization is moving closer to a point of irreconcilable, unstable equilibrium, as frighteningly increasing numbers of people trust nothing. Media, academia, and especially the governments are no longer held in high esteem. Regaining trust is often impossible after betrayal. However, transparency is essential to any healing process, and that is the essence of the Don Sullivan Show. Please listen to the team explore, probe, and debate cutting-edge science, technology, and computing. Play ball! Hello, folks, and welcome once again to the Don Sullivan Show. And believe it or not, today I'm actually sitting in an office as opposed to walking through a campground or sitting on a cruise ship or climbing up a mountain or dropping down a canyon or being under surgery or whatever else that we do here on the Don Sullivan Show, which is pretty much everything under the umbrella of science, technology, and computing. And today we're going to actually get back to our core competency, which is modern computing. And you all know that I don't like to use the word or phrase artificial intelligence because I believe it's a cartoon phrase stole from the Jetsons in the 1950s. But I will use the term quantum computing, which is really going to change the world, as opposed to a lot of huge amount of processing with a lot of arithmetic and data, which is what we refer to as artificial intelligence. So to that end, my buddy Steve, Jersey Steve, is here today, as well as Tony Foster, a fan favorite of the Don Sullivan Show and a very, very good friend to the show. And he's going to be on this and probably many other episodes as we move along in the journey of the Don Sullivan Show. And we're just going to have a lot of fun today because we already talked about it off camera in the euphemistic and legendary green room before the show. We talked about how Tony is going to spring some interesting things on us that are going to challenge some of my presumptions in regards to what quantum computing is. I imagine specifically in regards to quantum physics, which I'm going to give you a 5-minute lecture on. Even though Niels Bohr and Albert Einstein spent about 50 years on it, I'm going to give you a 5-minute lecture on it. But before we start, let's say hello again, even though you've been on for a few episodes, or at least live. Let's say hello to my friend and co-worker and kindred spirit in watching, Mr. Jersey Steve. Say hello, Steve.
Thank you, Don. Greetings from the Garden State. Today's episode is brought to you by License Fortress, the industry's first and only software asset management firm to offer both a financial and legal guarantee at its highest level of service. Whether it's Oracle, Microsoft, or VMware, License Fortress helps organizations stay compliant, avoid audits, and save money. Learn more at licensefortress.com. And please support our producer by visiting axtinc.com. That's AXTINK.com. Subscribe to his YouTube channel and help support his efforts to create humorous animation. And, well, I don't know, Don. What should we? What should it be this week?
Well, we got to give some kudos to Digital Sunshine and Gina. You know, she's been on so many episodes. She is basically
absolutely
a sponsor, so we got to do that, right? So let's
folks should check out Digital Sunshine. And I know Bill has been collecting free condiments from restaurants recently. So I think
free. Splenda, ketchup, Heinz ketchup, and all of that.
Sure,
he's got a whole closet, or at least a storage box for it.
I think it's spread into the kitchen, but we should support that as well.
Is he collecting the little paper cups too that you can squeeze the ketchup into?
Well, if I remember correctly, he did go to Fuddruckers the other night.
I got a feeling the thought hasn't gone that deep there, Tony. So, Tony, say hello and let's reintroduce yourself again.
Hello, Don. Hello, Jersey Steve. It's good to be back on the show. Thanks for having me. I'm Tony Foster. I work at Dell, just that small little tech company. And yeah, I've been doing that for quite a while now. I think 14 years at this point. So yeah, if it's virtualization or computers or something, I'm probably doing it. And this is the latest thing I'm turning into.
It used to be something to change the world, right? Now it's kind of like
table stakes.
Necessary. Yeah, something,
Yeah, it's like water or air, basically.
Yeah,
it's just there.
I wrote a book on Oracle and virtualization 12 years ago, and I thought it was going to be the standard for the world. It was the standard for the world for 12 years ago, but I don't know about now. People still read it. I still get a check every quarter for it, so you know.
Oh, there you go.
All right, nice. So our lawyers, the vast law firm that we have, including the frequent guest John Campbell, insist that I read the obligatory disclaimer, and I will. All statements by the host and the guest on the Don Sullivan Show are the personal opinions of the host and the guests, who all agree that the following content is the property of Analytics LLC to be used publicly and exclusively on the Don Sullivan Show. Well, folks, what is not opinion is the basic physics that I'm going to spend the next 3 to 5 minutes on, and that is of quantum physics. Since this particular episode is going to focus on quantum computing, we should talk about the whole idea of quanta. So sometime in the early part of the 20th century, one Albert Einstein won a Nobel Prize. And no, it wasn't for special relativity or general relativity, which described gravity. Special relativity basically describing E equals mc squared and all of that good stuff that is really interesting if you take a first level college physics class. What he won the Nobel Prize for was something called the photoelectric effect. I think that was probably because they felt embarrassed that they didn't give him the Nobel Prize for special relativity. But what the photoelectric effect showed was that light was actually transmitted in discrete packets that could be defined as a certain amount of energy, which was referred to as quanta. And that was then very well known. And over the next multiple decades, various different scientists, physicists, including one Niels Bohr, who actually had a rivalry with Einstein, came up with the concept of quantum physics, that all particles were quantified as quanta, but that there was all kinds of weird stuff that went on with that quanta. In other words, another guy named Schrodinger, who did a little bit more than played around with cats, had this idea that he would mathematically use what was called a second-order partial differential equation. Okay, different episode of the Don Sullivan Show, but he used it to come up with what was referred to as the Schrodinger equation, which described the duality between a wave and a particle. Amazingly, that Schrodinger equation describes all wave behavior, even waves in the ocean. But it also describes that wave-particle duality, meaning a single particle, a single photon of light, is both a wave and a particle, which has the bizarre implication that we can understand where a particle exists to a certain extent, but we only can understand it from a probabilistic perspective. Along with those concepts is the idea of commutators, which have different properties associated with each commutator, which are mutually exclusive in terms of knowing them, meaning a particular particle's momentum and its position. We can't understand both at the same time because the act of actually observing something changes it. Bizarre as that sounds. So the point is that with Schrodinger's cat, as bizarre as that was, Schrodinger postulated through the Schrodinger equation that there was a certain non-zero possibility that a cat in a box could all of a sudden appear outside the box, and vice versa. So as bizarre as all that is, that's the concepts that will be applied and are being applied towards what truly is a life and history-changing concept, soon to be productized, of quantum computing. Along with nuclear fusion, truly will change the world. That is, if we don't destroy it in the next election cycle, which is highly probable. We won't go into that. But this is incredibly wonderful scientific stuff overall. So with that 5-minute description of quantum physics, I want to bring in Tony here to describe how this applies, or if I'm just totally off base, but how this applies to modern computing, quantum computing. And again, differentiate, please, between the sort of silliness of artificial intelligence or whatever else we want to refer to as modern computing, because this really is space age, next century, next millennia computing, quantum computing. Take it away, Tony. Tell me where I'm wrong.
Awesome. So, yes, quantum is the next big thing on the horizon. If you've seen the stock market, quantum stocks have gone through the roof this year. It is the up-and-coming exciting thing.
Give me some examples of those. Who are they?
So, for example, IonQ or Ionic, I don't know which way you say the name. They build quantum computers. Regatta, I hope I pronounced it correctly. They build quantum computing systems. And then there are several other ones out there. And
Google and Microsoft are enormous investors, right?
Yes. And IBM has their quantum computer, and lots of people are trying to build quantum computers right now. So it's incredibly popular, and a lot of people want into it because it's going to be a very exciting area for whoever has the first commercially viable quantum computer. So, yes, it's something that excites me. It's something that hopefully excites your audience. It's something that will be a major change and shift for not only the computer industry, but everything everybody does related to electronics. And we'll talk about that more here in a bit.
Yeah, Tony, I've tried to give the audience this basic understanding of quantum computing without dropping them into Schrodinger's rabbit hole. Tell us how this applies to modern computing and what it really means.
Gotcha. So with quantum computing, we have something that's slightly different than traditional computing. And you alluded to this in your quick overview. So with quantum computing, we have what's called a qubit. In standard,
what the hell is a qubit? That's what we wanted to start with.
Well, I want to back up first. I want to put a couple of things on the table so that we have both of them.
I will wait with bated breath. I've been trying to figure out what qubit is for a long time. We need the context,
John. He's setting it up.
I want to set this up for everybody so that everybody can go along with us. So your traditional computers, they are 1 and 0s. That's all they operate on. They are binary. They are very discrete, very, very fact-based, right?
So this has nothing to do with the Patek Philippe $100,000 watch of a Qubits. I just want to make sure of that for you people out there. Okay, if you're tuning in to hear another watch episode, that ain't it. Go back, go for it, Tony.
Cool. So binary 1s and 0s, very discrete, very factual, very, very good at traditional mathematics and fact-based, repeatable results.
Deterministic, you would say?
I'd say deterministic. That is a wonderful word for this. They are very, very deterministic. 1 + 1 always equals 2. So, yes. Whereas in the quantum world, 1 + 1 may not always equal 2 because it depends on the context. So,
okay,
yes.
This is eerily starting to sound like a case before the Supreme Court, but go ahead.
It probably does sound eerily like a case
Your
before
Honor?
the Supreme Court.
Yeah.
So,
Your Honor, this has serious discriminatory aspects of it. Some people just don't believe 1 + 1 = 2, and you have no right to tell them they do. All right, I digress. Go ahead, Tony.
You are all fine with that, Don, because 1 + 1 may not actually equal 2. So we've got this idea of a qubit. And a qubit is made up of atomic material. And depending on how your atomic computer is created, your quantum computer is created, depends on what that material actually is. But we have these atoms. And we'll just go with atoms for right now because everybody understands what an atom is. So we're going to take an atom and we're going to read its state. And before we read its state or anything, and I'm going to use a different analogy than most people do, because most people use flipping a coin. You take an atom and you start spinning it, and we're going to analyze that spin. And while it's spinning, it's sort of like a piece of bread falling off the table that has butter on it. Which side is going to land up? Is it going to be butter side up, or is it going to be butter side down and a mess on your floor? And
I took my grandkid to breakfast today. It was definitely butter side on the floor, but that's another story.
Yes, well, that butter side on the floor. That's what happened when it finally landed. While it's spinning, this is where our qubit is. Our qubit is this atom or set of atoms that are spinning. We don't know whether it's butter side up or butter side down. It's in a unknown state.
Undetermined state. How do you spin the atoms, Tony?
So there are a bunch of different ways you can spin atoms. Lasers are common. So we can find defects in diamonds and hit them with a laser and do quantum mechanics that way. We can use supercooled liquids and hit them with electrons on a supercooled plane, which comes into the whole chandelier idea, and see how they're spinning that way. And all of a sudden I am forgetting the third way. But there are 3 different ways you can spin your atoms. And they're going to spin. We've got our toast spinning in the air. We don't know what's going to happen yet. So that's our qubit. And we're going to wait for it to get to a point where we're ready, and then we're going to get its state. Now, going back to what Don said, as soon as we grab that state, the wave function of it collapses, and we've observed it, and everything collapses.
So Schrodinger equation doesn't apply at that point, or it's got to be at least parameterized?
Maybe when it's spinning, but then as soon as we look, it becomes, it has to be one or the other, right?
It has to. Its
as soon as we
probability of one or the other is what we're actually going to be getting.
Gotcha.
So quantum computing is probabilistic in nature. What is the probability of this happening? The probability of the toast landing butter side down is 60%. The probability of the toast landing butter side up is 40%. And so we can collect that, and I don't want to jump ahead here, Don, but that gets into the whole wave function of our qubit. We can look at the waves this is generating and measure those waves and figure out what the probability of our qubit going one way or another is.
Okay, but again, let's get back to the original point there. The act of observing them is going to change it.
So that's an important process. That's an important part of how they work, the observation of the state of each atom or set of atoms.
Set of atoms, yes. And go ahead.
I was going to ask, so instead of a traditional computer that uses ones and zeros in a binary system, that's kind of either being replaced or augmented with the qubits that are spinning and observing the state and the probability of that state?
Yes, that is correct. We are going to observe that probability, and chances are we're going to observe that probability over a much wider state than just 1 and 0, because you have multiple instances of how this could play out. So if I
more of a spectrum than one or the other.
Correct. So let's say, and qubits are typically done in 4 pieces or 4 atoms. So let's say I drop toast off the edge of a table 4 times. I've got a spectrum of 16 pieces of probability there.
Okay.
So 16 potential outcomes in just in
16
terms of the
potential
binary
outcomes.
chance.
Yes.
Gotcha.
Go ahead.
How does this make computation faster or scale more? I guess is my next question that I'm curious about. How is this better than how is this better than traditional computers, I guess?
So for large scale simulations, this is awesome. For big problems, this is awesome. For 1 + 1 = 2, this is not awesome.
And we've already decided
Gotcha.
that isn't the case anymore anyway,
Yes.
so we can move on.
Exactly. Because 1 + 1 = 2, that's something
It's
that's
irrelevant,
done very
even if it was
efficiently.
true. Yeah.
Yes, it's done very efficiently by standard computers. We don't need quantum computers to crack this.
However, we get closer when we're talking about 2 to the 4th power and we have 16 possibilities. It becomes more interesting. Yeah.
It becomes much more interesting. And if we bring a bunch of qubits together, all of a sudden it gets even more interesting, because now we can start arranging these qubits in different orders and stuff and going, okay, we have 2 to the 4th power here, and another 2 to the 4th, and another 2 to the 4th, and another 2 to the 4th. And basically, once we get about 1,000 qubits, we can represent most anything we want on the face of the Earth.
Well, at that
1,000
point,
qubits.
I mean, you're getting close to the number of moves in a chess game, which is like equal to the number of atoms in the universe. So
Exactly.
And what I would ask you, though, is if we can, at this point, transistors are almost on the nanometer side. In fact, they are. We have transistors that are on nanometer side. And actually getting that information out of them and reading it again individually or reading it in mass seems like an overwhelming task. And in fact, it seems like it's magic. It seems like kabuki at this point. I mean,
do we use AI to do the reading?
Interpreted. Because what you just say makes total sense to me, and I hope the vast audience of the Don Sullivan Show, from a mathematical perspective, that there is an entire spectrum, almost an analog spectrum of possibilities, as opposed to a binary digital, or even something that was power of 8 rather than power of 2 type, or hexagonal as opposed to binary. All that is interesting. This is literally infinite in scale. If you can read it and interpret it, that seems like magic to me.
Yes. Well, so I'll throw this out here, and it's going to actually help with this. It's another analogy. So let's say I've got a nice little koi pond in my backyard. Or since it's summer right now, I've got a kiddie pool in my backyard filled with water. Filled with water, no wind, no kids playing in it right now. No toast floating in it either.
Ah, nice.
Yeah.
Fancy.
No, fortunately, the toast missed the pool in the backyard. So that's good.
Yes.
Very classy.
Yes.
Yes. Well, what do you expect from a little round blue kiddie pool?
Mm.
Now, that water is perfectly flat and everything. Nothing's in there. So if I throw a pebble, we'll say a 1 gram pebble, into that water, all of a sudden I'm going to have ripples going across the surface of the water, right?
You are.
I think everybody would agree with that.
Yep.
Described by the Schrödinger equation within levels of mathematical perfection.
Exactly.
As long as you knew what the size and the velocity of that pebble was and the angle at which it hit the water and where it hit the water, all the parameters involved, you could get a 100% accurate result out of the Schrödinger equation for that wave behavior.
Exactly. And so that is very much what we're doing with quantum computing. We're tossing pebbles. We've got nice waveforms that are happening. And
but here we're talking about nearly an infinite amount. But I'm sorry to interrupt you, but go ahead.
Oh, no. You're fine. Yes, it is an infinite amount. And we've got other waves going on outside of those. So that computer fan that's out next to the quantum computer creating airwaves, it's creating noise and stuff in that as well. So we're going to have a hard time calculating that. That's some of the reasons why you see supercooled chandelier systems that are looking at molecules, because the waves are going to slow down so that we can get a better measurement.
Better read on it. Interesting.
Exactly. But we can apply Schrodinger's measurements to these wave functions and read this information in. So it's not magic.
What do we do with it to interpret it? See, this is where I fall off the table here. I don't know. I've read theories before that it's that a single atom, a hydrogen atom, and the fact that every proton in the universe is exactly the same is God in that way. A Carl Sagan kind of look at things, and that they're all the same, and that every particle in the universe knows about every other thing that has ever happened. In fact, if you could read the actual resonance of every particle in the universe, you could see everything else that has ever happened in the universe. You could see where, who shot Kennedy easily, because it's all in there. And the reason I bring up such an esoteric concept is that everything is affecting this. Everything. And so therefore the interpretation has to include every parameter. And so how do you do it?
So great question. I don't have a good answer on that because, I am not a physics major. So I don't actually know the exact function and stuff.
Well, okay. How does it work from the computing perspective? And I guess the question is good enough, especially since we are getting into Schrodinger's rat hole right now.
We are.
You led us there, Don.
It's good enough to say that at this point, the interpretation of that literally infinite wave resonance from the qubits gives us relevant information that, from a practical perspective, on a level of modern computing, is orders of magnitude more useful than anything we've ever seen.
Yes, absolutely.
It's still non-probabilistic, though. Is that correct?
No, it's probabilistic, but it's probability.
It's non-determined. It's non-deterministic. It's
not in an absolute sense, but it is 1 to the 100th power on, right? Something along
Gotcha.
Yes.
Not 1, 2 to the 100th power. 1 to the 100th power would be 1. But
I feel like I'm watching an episode of that show, that German Netflix show, Dark, where I'm trying to...
Do not compare me to Bill Nye, the science guy, ever, all right?
You clearly don't know what show I'm referencing, because it has nothing to do with Bill Nye, the science guy.
And I would have shut down this episode.
Do you like him, or do you have beef with you have beef with him?
I wouldn't have beef with him. That would be too dangerous for him. So,
Fair enough.
Look, Pee-wee Herman would have done a better science show, okay? Okay, Bill, if you can hear me, sue me. That would be great. Great publicity for the Don Sullivan Show. Go ahead and sue me.
We're going to have to include this in the description.
You are the freaking Pee-wee Herman of the science world. All right,
I enjoy Pee-wee Herman, for the record.
Wow. So
that's a
Jersey
lot.
Steve, you got me doing what's called a donkey laugh.
Will not be cutting that part out.
So, nope, I'll leave it in. I will leave it in if you want.
Anyway.
Yeah.
I should get back to Don's original question.
Yes.
The whole wave function and everything is very, very important for the data that we're collecting.
How is it relevant to what we're going to do with these things, these quantum computers?
So,
and why are people going to make it? Why are there going to be multiple $1 trillion companies overnight from it? Which I know is going to happen.
Absolutely, it's going to happen. And the reason this is so important, collecting this data is so important, so relevant. Yes, our atoms are going to be influenced by everything. This is very much true and goes back to the idea of probabilistic results. So when you say 1 + 1 = 2 to a quantum computer, you're not always going to get 1 + 1 = 2. And for an example of that, let's say I said that in binary. 1 + 1 in binary does not equal 2. 2 does not exist in binary. You cannot get 1 + 1 = 2 in a true binary fashion. And so quantum computing is going to take note of that.
I think there are certain Supreme Court justices that might disagree with you on that, but that's,
that's neither here nor there. The reality, whether you want to admit it or not, the probabilistic reality is 1 + 1 does not always equal 2. It may equal 11, and that's okay.
Interesting. So
I really better shut up here. You keep going, Tony.
How hard is it to make these qubits, Tony? I mean, can Don and I get a little side action making some of these, or do you have to be
companies here? We got to get in on that action, right?
Yeah.
I wish it was that easy. I wish this is something I could go whip up in my garage. So if you've got a lot of high-powered lasers, a lot of liquid helium,
so you got to kind of hadron collider it a little bit. It's kind
not
of
really hadron collider it, but you got to either be able to supercool something.
500 degrees Fahrenheit for the liquid helium or something around those.
So it's about the super cooling is really important.
Yeah, that well, it depends on which way you want to do it, because I've been talking about the different ways. So if you're going to supercool it, then you're going to shoot electricity at your qubit and get all the spin measurements and everything. And that's one way to do it. And that involves a chandelier with tons of electrodes and everything coming into it.
That's the chandelier one. So, okay.
That's the chandelier one. Then there are things that look like they belong on, I don't know if you remember the old PBS television show of 321 Contact, where they had...
I'm looking it up.
So throwback there, yes, throwback from my childhood, where in the intro they had lasers and stuff bouncing all over the place with different mirrors and refractors and pass through things. That's another form, and typically that's done in a vacuum with flaws in diamonds.
Oh yeah,
and so that doesn't require the liquid cooling. But it has other things that are hard about it, such as what's known as error correction. And we'll talk about error correction here in just a second. And then the third way is we can actually build these like we build transistors and everything. We can actually fab up chips. So go through and fabricate a computer chip, much like we fabricate a central processing unit for an actual computer.
So is this done by most of the chip makers? Is this Taiwan Semiconductor, or is this something in a specialized HP or IBM construction, or super secret projects from Google?
I bet.
So it's not a super secret project. I actually went to NVIDIA GTC this past spring. And
I did not. I meant to, but I did not.
I know. I didn't see you. I missed you there, Don.
Yeah, I didn't go. I was somewhere else in the world. I don't know where. Doing a podcast.
You're probably on the mountain.
Yeah, probably.
I got to hang out in the quantum computing hotel.
No, I was during the wrath of Kilimanjaro. That was during the wrath of Kilimanjaro.
Probably a good reason to not be
there.
The
wrath of the volcano. Yeah, you didn't want me there then.
Shigella, right?
Yes,
yep.
Yes.
The Shigella episode. So they had a quantum computing hotel. So
they had a hotel where all of the quantum computing stuff was going on. All of the presentations, all of these great minds were talking about their different quantum systems and how they all worked. That's where I spent a lot of my time at GTC, was with the quantum nuts. The quantum nuts, we looked at all of the different things that were part of it. Do I need to pause?
No, go ahead. We're good.
Okay.
Nope, you're good.
Cool.
Sorry, we just had a visitor here on the Don Sullivan Show come in to make a comment about probabilistic issues having to do with whether or not he has lunch right away or not. But we're going to have to wait 20 minutes for that. So go ahead.
I've got a Schrodinger's cat thing with the lunch going
definitely.
on.
So Tom, please
yes.
continue.
Definitely. So, yeah, all of these great people and everything were in there talking about quantum computing. And that was one of the big things that they were talking about. And I think it was D-Wave. I probably got it wrong, so my apologies on that. That has a quantum computing chip that they manufacture like a transistor.
How
Very,
big is
very
it?
cool. This is
Not- it's
about
not
the
only
size
the
of a
size-
refrigerator.
Oh, okay. The
The
computer.
refrigerator?
whole
Yeah,
unit
yeah.
is complete with networking and everything, is about the size of a refrigerator.
So you're not
So these
talking
are
about just a
big.
transistor. You're talking about a big single.
So
At
I
this
think
point, there's little distinction between the chip and the computer, I guess.
this is true.
Yeah.
I think their unit currently has 16 qubits running in it. Now that you're like, that's a lot. We can do a lot with 16 qubits. One of the things that you have to do with these environments is you have to do what's called error correction. So remember we threw that stone into the kiddie pool in my backyard?
Mm-hmm.
Now let's say we throw 3 stones all at once into the kiddie pool at my backyard. But we are only interested in one of those stones.
Got to cancel the others out somehow.
We've got
that.
Yeah, we've got to come up with a way to figure out how to get rid of the other stones creating the waves. And that's part of the idea behind error correction. There's more to it than that, but that's the principal idea. Is there's all this noise happening, the fans running inside the computer room, vibrations from an earthquake or anything else.
Everything that's happening in the universe.
Yes.
Well, and this seems to align with how we look out into space and having to correct for certain things that are going on as well, using those big telescopes and sophisticated technology. You know, if we're trying to look at a certain redshift, or, hey, you know, we need to get rid of this interference or this background radiation so we can lock onto this. That's a lot, though. That's very complicated.
Yes.
Well, the filters become much more important and much more processing demanding than anything else.
Yes. And so that's what everybody's dealing with right now, is taking care of error correction, whether it's with these giant chandeliers and isolation and everything, and having error correcting qubits so that they can get maybe a dozen qubits all working together. And maintaining state long enough to actually process something, or silica-based qubits running long enough that we can process it and address any of the noise from everything. So it's a very interesting thing to study, and first mover advantage goes to the person who figures out how to deal with all the noise.
This is one of the things I said in regards to modern computing, but particularly this, is that it is a rare point in history in which mathematics as a discipline doesn't precede the actual technology by 200 to 300 years. During Newton's time was an example, and he had to actually discover calculus, and Leibniz did it at the same time, I know, but he had to discover calculus to prove the Principia But for the most part, mathematics is hundreds of years ahead of, because it's so abstract, ahead of technology. And I think we're at a point right now that, there's lots of mathematics that mathematicians sitting in basements and universities have no idea how it would possibly apply. But right now we're looking at mathematics that can help us understand how to interpret that error correction and the filtering properly to be able to, as I was starting this segment on, truly interpret the actual data we're getting. Do you think that's sort of fair?
Absolutely, that's fair. And one of the things that ties into this that we haven't touched on, haven't even said it once since your introduction, I think, is AI. We can take the results.
There's that term again.
Dun, dun, dun. Yes, we can take those results that we're getting from the quantum systems and use AI and that discrete math against our probabilistic results and go, hey, iterate this.
Infinitum.
Yes, and figure out what the noise is. We know these are the functions, but we've got to apply a million functions to this to isolate what we're looking for correctly. A human can't do a million functions, so yeah.
So they're going, AI and quantum go together, it sounds like.
Well, they can be complementary in this.
At
They
that
can
scale.
be complementary, yes.
Okay.
So let's look at some actual practical implications. And the horror story out there that most people of the Don Sullivan Show and others have heard of is that once a quantum computer is a real product, that every password on Earth is going to be totally irrelevant. That maybe biometrics might make sense, but every password that exists, no matter how big it is, no matter how sophisticated the hashing algorithm, is going to be useless. Is that
they got good ones, Don. They've got exclamation marks in them. I don't know.
I don't know.
Tony was wagging. Tony was shaking his head.
Tony, tell me, is this
Jersey Steven, Don, I hope the mics did not pick up my eye roll.
Well, they did. They did.
On a quantum level, perhaps.
Okay.
Too much? You think that's it's just a horror story that buries?
Is that overblown?
Is it tabloid from a cable news show that I've been hearing too much of?
So this is the thing that everybody in quantum either loves to talk about or hates to talk about. And the reason is there are a certain set of passwords that are vulnerable. A certain set of ciphers and keys and stuff used in encryption are vulnerable to quantum. And the reason for that's very, very simple. We're talking probabilistic here, and we're talking really large prime numbers. Well, quantum computing can calculate prime numbers very, very quickly and go the probability of this prime number, because remember, piece of toast sliding off the table, what side's it going to land on? If we have, let's say, 100 qubits that we can use, we can calculate all of the prime numbers and their likely position in this instantaneously.
So you are telling me, though, at least the way I'm hearing it, is that all hash-based security is vulnerable.
That there's the distinction there. Hash-based security.
So we need quantum proof or quantum Can quantum help us with new encryption?
It actually can.
So even if hashing is out the window, we have a new approach. And this goes to my next question.
But we have to get there first.
What positive products can come out of this?
So, yeah, there are a lot of positive products that can come out of this. And I think that's actually where quantum computing shines. And everybody gets hung up on, our hash-based algorithms are going to... it's all security, and they're going to be compromised, and people are going to be able to look at my tax returns from 2005. Oh dear, we've got to put a stop to this. That's what everybody's concerned about. the reality, the potential that quantum computing actually unlocks is amazing. So I'm just going to start running down a bunch of them. From a medical perspective, this becomes very, very interesting. We can calculate drugs or the probabilities that drugs will work very quickly. We can formulate new things we haven't even thought of.
So
with
the
quantum
overall
computing.
FDA testing processes and protocols can be dropped from 20 years to seconds.
Weeks, hopefully.
Weeks.
Perhaps diagnostics as well, patient
Running
diagnosis.
simulations, at least. It could be virtually immediate.
Absolutely. Yes. What's the
That's
result
cool.
of combining these three atoms in this particular way, in this particular order,
These
and
three
making sure
compounds,
there's
which are drugs and so on,
Exactly.
all the permutations.
Yes. What's the result going to be? What's the probability that this drug is going to work?
Yeah, the poor doctors would always ask about the counter indications and have to guess at all of them because the three body. Well, there you go. There's the big one. Can we possibly get to a point of solving the three body problem, which is a whole other Don Sullivan show, but it's never
also
been solved,
on Netflix.
Right? Yeah,
that's another Netflix one, Don.
Well, we can do that. If Netflix wants to give me a call, we'll do a whole series on the three body problem. But go ahead, Tony.
No, they have a show called that.
Well, we can do better. We can do a real science show. Okay, go ahead.
So, yes, we can do drug discovery. So the whole let's make lives better, let's extend lives, let's make things cheaper, that's something that's going to be unlocked with a robust quantum computing platform. We can do security. We talked about security already. I am going to bring it up just because it makes things very, very difficult.
You need to transition into a new paradigm of security worldwide. That may or may not include biometrics, but point is, it's not going to eliminate the existence of potential for security. It may just cause it to have to change and transition quickly.
It's going to have to change and transition quickly. And the real simple reason for this is I'm going to start with the atomic clock. We've got an atomic clock. What's an atomic clock monitoring? The spin of an atom, right? So when we send a message, we know where that atom was, what time it was, down to the atomic level, when that message left, and when that message arrives. We can use quantum cryptography to encrypt that message, and we can tell if anybody's messed with it just because of that time. We'll know if it got a 1 second delay. We'll know if the quantum signature of that message has changed in any way.
Going full circle with the show, we will be able to tell if it has been observed.
We will be able to tell if it's been observed. And so we can ensure transmission of messages securely from one point to another, regardless of distance. So it's going to be very, very powerful, and it's going to be very difficult for somebody to be able to crack that with either conventional systems or quantum systems. So that's
so what else? What else? What other products?
What about playing the stock market? Could I become kind of like Biff in Back to the Future?
Sports gambling.
Or sports gambling.
Yankees have lost 7 straight games in a row. Can I? Is it going to be a coin flip? If they're going to lose 8, or do they just suck? So, and then can I bet on them losing 8 in a row? I don't bet at all in sports, but just euphemistically speaking,
you could, in theory. I don't know if that's the greatest approach.
Yeah, probably not.
I can use a GPU, which is a whole lot smaller and a whole lot cheaper than a quantum computer to do the probabilistic
it doesn't
outcomes.
generate any more heat than's in my father's head about this right now, but that's another.
That's an entirely different thing. I can't help with that.
Episode of the Don Sullivan Show. How my father's head generates heat when the Yankees play like they did today. But go ahead.
Needs super cooling like the computers.
Well, and so that's another area where we can get into some really cool stuff with quantum. We can start calculating the most efficient forms and patterns to cool things with or heat things up, whatever we need to do. So all of these data centers and stuff are producing tons of heat and consuming water and everything else. We can apply quantum computing to this to go, what is the most efficient way to cool this? Do we need to come up with a new supercoolant, going back to some of the previous stuff where I talked about medicine? Same thing applies to coolant systems. Do we need to do some sort of weird fold on our aluminum to get the best heat dissipation? What's the best way to do this?
Material science, which is a favorite of the Don Sullivan Show and me, can be the simulations again can be just amplified, and therefore the testing times.
And then probably my favorite
multiple
is
orders of magnitude.
Atomic energy.
Fusion time.
Yes.
All right, let's hear it.
Yes, one of the things with fusion, and Don, I think you've talked about fusion before on your show.
Oh, I certainly have. We're going to have a whole series on it soon.
Woohoo! So, with fusion, it's very hard to maintain the reaction in a stable state. It takes a ton of computers.
There's 40 companies right now that are using magnetic bottles or some version of that to try to productize, and so we're getting there, man. We are getting there.
We're getting there. But to maintain its stability and everything, right now it's 40 computers or thereabouts.
40 companies that are doing
40 companies and tons of computers and tons of wires and tons of cables and lasers and stuff. And it's not commercially viable yet.
No.
They're hoping it will be. Those 40 companies are hoping it will be commercially viable.
Oh, the level of investment is enormous. Yeah, so we're definitely on the way there, but we're not there yet.
And we can take quantum computing and go, how can we make this more stable?
So all these things fit together. That's a great way to
all of them fit together. And this is the true power of quantum computing. It's not, oh my gosh, my tax returns are going to be exposed because they're encrypted using hashing algorithms. It's look at all of the other cool stuff that we're going to be able to unlock. This is probably going to change space travel, how we move about in space. How do we efficiently go from the surface of the Earth, pulling against gravity, to orbit into deep space? We can look at all of these different transitional periods and all of the movement and stuff and figure out the most effective way to go from each of these stations.
Call Tom Hanks. Get ready for the movie, too.
Oh, yeah. Another Apollo.
Right. Guys, we are pushing it, and the Don Sullivan audience can't handle more than an hour. So I'm going to skip a few questions here. Tony, if you don't mind, we're going to have you back in about a month to go through after a couple of other episodes to do a second part for this, because this is just too fascinating, and we'll see where things are at then. But I do want to end this episode. Again, I'm going to skip a couple of things I wanted to talk about. But I want to end this episode, and I'm going to put you on the spot totally, and we will hold you to that and ridicule you as appropriate if this does not happen in the future. But where do you see products happening in the relatively near future? Microsoft says that Majorana, if I pronounce it correctly, too.
Majora.
Majora? It's kind of, Majora. We'll call it that. Is going to be productized in 2029. That's what they are publicly saying right now. And they've had massive breakthroughs. They say it's going to be productized. Who knows why they say that, but what do you think?
I
2029, I
suspect,
said. Yeah, go ahead.
I suspect, and this is me looking at the toast spinning in air, which side's it going to land on? I suspect that it will probably be 2030 when Majora becomes available. I'm expecting some extra flips and stuff in there with their qubits that's going to push it a few months, not a lot, but a few months into 2030 instead of 2029.
All right, this is amazing stuff, and so we will hold you to that particular prediction, Tony, and because I'm right now putting in a 2030 call order on Microsoft, or December 2029.
He just wants stock timing.
It'll be your fault if I lose my watch collection. Okay, so
here's the problem, Don. We didn't talk about anybody else in the marketplace.
Well, we're going to in the next episode. We're going to have you on right when Steven and I get back.
It'd be easier if we had a quantum computer to make these predictions. Is it going to be like a cloud service, Tony, or an actual appliance, or any ideas on that?
So again, putting on my big crystal ball hat and trying to figure out what this is going to look like. The very first ones, and technically right now you can get quantum computing time from IBM as a service.
You can actually buy it now?
You can buy quantum computing time. It's mainly for research. You don't have enough qubits to do a whole lot with.
Okay.
From IBM, as I understand it.
That's amazing.
Yes.
How much? Do you know how much it costs? Like, is it really expensive?
Know how much it costs. I don't know how much it costs.
It may be free because they just want the testing data.
It's something I can't afford personally. So obviously, I'm not able to hook it up to my home lab.
Don, put your credit card in. Let's make some bets and try and get a good ROI.
So I'm going to be, I'll tell you, I'm feeling this now because in a couple of weeks, I'm going to be 64 and Paul McCartney is going to personally sing to me when I'm 64.
Exciting.
Awesome.
And he is, I've heard that. So I really wish I was much younger. So, I could see how this eventually turns out in 30 or 40 years because I figured by then it'll be done no matter how many mountains I climb. But folks, we're going to end this right now, and we're going to keep you right on the edge of your seat for the questions that I had that I wasn't able to pose to Tony. The greater predictions, the other companies. That's the one that we're really going to talk about. The other companies that are getting very, very close, and we're going to make sure that when we get on the panel discussion about Musk versus Altman later this week, Tony's not going to be allowed to talk about any of this stuff yet because we're going to keep you on the edge of your seats. Mm-hmm. But we're going to end it here. Is there anything you have to add before we leave, Tony, that you are just chopping
final
at the
words?
Bit? Yeah, final words.
You're leaving the toast spinning in the air.
Okay.
That's
Our
perfect.
viewers and listeners are not going to know where the toast lands.
And I got a feeling that ripple in the pool is going to still be happening when we get back on. And with all due apologies to anybody that I ridiculed, which was many on this particular show, we will save it until the next show. That is if I'm not sued into oblivion yet. But folks, I will tell you that no matter what we're talking about, the highest level of modern computing or the highest mountains in the world or the lowest canyons or whether or not I'm under anesthesia still trying to talk. Remember, folks, the one thing that you always have to keep in mind when you're confronted with any situation is that all at-bats are situational. See ya.